This video is about approximating areas under curves, part 2 of 3 Riemann sums. Let me start here with just a general function f of x. So if I have some general function f of x, I'm going to make it look like this, why not? And we're going to find the area of the curve between A and B. So we want the area below the curve and above the x-axis, okay? So this is the area that we're going to be finding right in here. Well, we know that we can approximate that by taking our interval from A to B and breaking it up into subintervals. So here's my function f of x, and the first thing that I would like to do is partition the interval from A to B into n subintervals. So in this particular case, each subinterval is going to be delta x. Delta x is going to be b minus a. That's the total distance from A to B, divided by n. Here, a is going to be our x sub 0, and b is going to be our x sub n. The next thing we're going to do is we're going to find our grid points. Our grid points are each of the end points of the intervals. So we're going to have x sub 0, x sub 1, x sub 2, all the way up to x sub n. Now, in each subinterval, each kth subinterval, we're going to choose some point, and it can be any point. We're going to talk about some specific things later, but it can be any point in the interval. We're going to call that x sub k star, so that will be the point that we choose in the kth interval, and we build a rectangle. So then we're going to find all of the areas of the rectangle, and then we're going to add them together. So what is that going to look like? That is going to look like f of x sub 1 star times delta x plus f of x sub 2 star delta x all the way up to f of x sub n star delta x. So keep in mind, for each one of these, let's say this is our first subinterval, okay? And I choose this point as my x sub 1 star. Then that's the height of the rectangle. The function value at x sub 1 is the height of the rectangle. And the width of the rectangle from here to here is the delta x. So I can choose any point that I want. I could choose this point, and then that would be the height of this rectangle, right? So that would be our second subinterval, and we would choose x sub 2 star, that would be some point in that subinterval. Find the function value, that's the height of the rectangle, and then multiply by the width of the rectangle. So let's take a look at a couple of notable Riemann sums that so let's just look at the definition of a Riemann sum. Suppose we have a function defined on a closed interval from a to b. We divide it into n subintervals of equal length, and the length of the subinterval is delta x. We pick any point in the subinterval, and then we build these rectangles and we add them up. So there's a couple of Riemann sums that are special, so to speak, and that is a left, right, or midpoint Riemann sum, and there are some great little illustrations here. So let's take a look. On this left-hand Riemann sum, you'll notice that for each one of these rectangles, it's the left-hand corner of the subinterval that is the height of the rectangle every single time. For the right-hand sum, you'll notice that it's always the upper right corner of the rectangle that gives the height. And for this one here, we're always going to take our subinterval, we'll break it in half, and we'll use the midpoint of every subinterval to find the height of our rectangle. So keep in mind that if we're doing a left-hand Riemann sum, then the first, how do I say this? Let me make this a little bit bigger, okay? Let's make this really small up in the corner, and I'm going to draw a picture of a left-hand Riemann sum. So I'm just going to draw a general function, f of x, from A to B. So this is the area that we want to find. And I want to find my subinterval. We're going to use n equals 4. So our delta x is going to be b minus a over 4. And let me just draw this in 1, 2, 3, 4. Now if we're doing a left-hand Riemann sum, then the left hand of each rectangle, the left hand, the corner, the left corner is going to be the height of the rectangle that we're going to use. So we're going to find these 4 areas and add them up. So let's call this, we know that a is x sub 0, 1, 2, 3, and 4. And so our left-hand Riemann sum is going to be the function value at x sub 0 times delta x. And then the function value, the second rectangle, has a height at f of x sub 1. And then all the way up to f of x sub 3 delta x, because that's the height of the last rectangle. Now think about that for a second. I'm going to draw over this in black. Let's say I wanted to do a right-hand Riemann sum. Then for each of these rectangles, the height of the rectangle would be the right-hand corner of the rectangle, upper right. And that's going to look a little different, right? Oh, this one's going to be way up here. All right, so in that case, our sum is going to be similar, but what is our first height of our rectangle? Well, in this case, our first height is at x sub 1, then x sub 2, and then all the way up to x sub 4. So you'll notice that the grid points that we're using here differ depending on if we're doing a right-hand sum or a left-hand sum. Let's say that we have some function, f of x, and we want to approximate using Riemann sums. So the first thing that we're going to do is we're going to partition our interval from A to B, into n subintervals. That's going to be a delta x. So delta x is going to be the length of the interval, b minus a, divided by n, where a sub 0, back up again, a is our x sub 0, and b is our x sub n, so the beginning and the end. Then we're going to find what we call our grid points. The grid points are the end points of each interval. And we're going to label those x sub 0, x sub 1, x sub 2, all the way up to x sub n. Then, in each subinterval, in the kth subinterval, we're going to choose any point, and I can explain this in a little bit, but we're going to choose any point in the interval, and we're going to call that x sub k star, and then we're going to build a rectangle. Then we're going to find the areas of all of the rectangles. And we're going to add those together. Okay, what is that going to look like? That is going to look like, let me make this just a little bit smaller. That is going to look like f of x sub 1 star times delta x plus f x sub 2 star delta x all the way up to f x sub n star delta x. So what we're saying is this is going to be the height of the rectangle and we can use some point in the subinterval to determine that height. The width, however, for every single one of these has to be the same. This is going to be the height of the rectangle in the second subinterval. This is going to be the height of the rectangle in the nth subinterval. So what we like to do, so we have a couple of rules that we're going to use here using sigma notation. So if you remember, when you have this capital S, Greek letter S, and you have k equals 1 to n of some function. This here is the upper limit. This is the lower limit called the index. K, we could use k, I can use n. This is really a dummy variable, so it doesn't really matter what it is. However, I just made a boo-boo. If this is k, then this has to be k as well. So, because we're going to cycle through the k's. So basically what this means here is we're going to add f of 1 plus f of 2 all the way up to f of n. We're going to add those things up. So this is going to become really powerful for us in writing our Riemann sums a little cleaner. So you can see down here that for these three notable Riemann sums, left, right, and midpoint Riemann sums, we can just add all of the, from k equals 1 to n, we can add all of the function values times the delta x and add those all up together. Now, this expression here is not any different than these two expressions here, but what's different is the grid points that we're going to use. So let me see if I can give you a quick example of why we use what we use. So let's just say I have a function and I want to use right-hand endpoints. So I'm going to use the right-hand corner of each of these function values. And this here is going to be my delta x. So this is my function f of x, and a would be my x sub 0, x sub 1, x sub 2, x sub 3, which in this case would be b. So what we're going to do is look at this and say, well, my first rectangle, this rectangle right here, has a height of f of x plus 1, or not, sorry, of x sub 1, right? That's my first height right here. So f of x sub 1, and then the next one is f of x sub 2, and then I'm going to go up to f of x plus x sub 3. And I'm going to take each one of those and multiply by delta x. So this first grid point here, x sub 1, is really, we call it x sub k star, but it's really just a plus k delta x, where x begins at 1 and cycles through. So if k starts at 1, a, in this case, is 0. Well, actually, we never said that a was 0. So whatever a is, our first grid point is going to be a delta x away from that. And then our second grid point is going to be 2 delta x's away from that, and so on. And so that's why these things are different, because I think you can see that if I had done a left-hand Riemann sum, then the heights of these would have started here at a, then it would have been x sub 1, x sub 2, and we don't need x sub 3. So for a left-hand Riemann sum, your x sub k star is going to be a plus k minus 1 delta x. So that your first one, if you plug in k, you're not adding a delta x at all. You're just going to get a as your first left-hand endpoint. So that's again why those are different. Okay, let's take a look at an example. We want to look at the Riemann sum for cosine x from 0 to pi over 2. So just so we kind of get a handle on this, if this is pi over 2 and this is 1, cosine kind of goes like this. Afterwards, it'll go down, but we're not interested in that. We're just looking for this area. It looks like part of a slice of pizza, maybe. I don't know. So we're going to first find our length of our subinterval, which is called delta x, and that's b minus a over 2. So in this case, pi over 2 minus 0 over, I said 2, but I meant n. So divided by 6. This is going to give us pi over 12. So this is going to be 0, 1, 2, 3, 4, 5, 6. Each one of these intervals is going to be pi over 12. So this is 1 pi over 12, 2 pi over 12, which is pi over 6, pi over 4, pi over 3, and 5 pi over 12. So those are each of our grid points. Where's that? Where's that? Oh, here we go. 3.297 times pi over 12, and that's going to give me 0.86338. So let's just step back for a moment. I mean, I did this, off camera. I added those all up. But we can use our calculator to help us out there. So what we can do is we could put into our calculator into y1 cosine x, and then we could use a table set and make our starting value pi over 12, because I know that that's my first grid point, and then do my delta x as pi over 12 as well, and it'll make a nice list for me. All right, so this sigma notation, let's take a look. What does it mean? Let's look at one little example here. So this is the sum of all of the k squared plus 1s from 0 to 4. So what that means is we're starting with 0, and we're going to plug 0 in, and we're going to get 1. Now plugging 1 in, 1 plus 1 is going to give us 2. 2 is going to give us 5. 3 is going to give us 10. And 4 is going to give us 16 plus 1, which is 17. So in the end, this summation is 2735. Now, we had some rules here, and we're going to go over them in just a second, but this does not start at k equals 1, so I can't use those rules. But we're going to talk about how we can use those rules if we adjust for the k equals 0. All right, let's take a look. The first rule we have here is the sum of the constants. So k equals 1 to n of c. Keep in mind all of these start at k equals 1, and that's going to become important here, and I'll show you at the end why. But the sum of the constants is just the upper limit times the constant. So for example, if you did the sum of the 4s from k equals 1 to 7, you would just get 7 times 4, or 28. The next one says if you have a constant times a function, you can pull that constant out in front of the summation, like so. So you might have 5k, k equals 1 to 4. We can bring the 5 out in front and have just the sum of the k's, k equals 1 to 4. We'll come back to this in just a moment when we have the rule for the sum of the k's. For our next one, we have a sum of a sum or difference. We can take the sum of the first plus the sum of the second. These next few are very, very useful when we do our Riemann sums. The first one is the sum of the k's, and the sum of the k's from 1 to n is n times n plus 1 over 2. So if we come back up here, this would be 5 from the outside, then it would be 4 times 4 plus 1 over 2 for a total of 50. For the sum of the k squares, the formula is n times n plus 1 times 2n plus 1 all over 6. So an example there might be k equals 1 to 18 of the k squares, which 18 times 19 times 37 all over 6. Reducing a little bit, we can say 6 goes into 18 3 times, and we'll get a total of 2,109. Quite a lot easier than squaring 18 numbers and adding them up on our calculator. For the last rule, the sum of the k cubed, we have n squared times n plus 1 squared over 4. So an example might be k equals 1 to 6 of the k cubed. So 6 is our upper limit here, so we're going to get 6 squared, or 36, 7 squared, which is 49 over 4, and we'll get 441. So let's just do one example with all of these. For example, k equals 1 to 6 of the 3k squared plus 2k minus 1. In this particular case, we would take each term because we're using the sum or difference. So we'll have, bringing the 3 out in front, 3 times the sum of the k squares plus 2 times the sum of the k's minus the sum of the constants, k equals 1 to 6. This is going to give us 3, 6 times 7 times 13 all over 6, plus 2, and then 6 times 7 over 2 minus 6. And we can clean this up a little bit easily, which gives us 309. So the last thing before I finish up this slide is, how do we handle something if I don't start at 1? So just a quick example. Let's say, for example, I have the sum of the k equals 5 to 10 of the k squared. Well, I can find the sum of the k equals 1 to 10 of the k squared, but I only want 5 through 10, so I'm going to subtract off k equals 1 to 4 of the k squared. For example, here, if I have k equals 0 to 10 of the 3k, well, we know that 1 to 10, k equals 1 to 10 of the 3k I can find. So I just have to find out what is that first one at 0, which happens to be 0 in this case.